Hello, and welcome to this presentation of the STM32C0 power controller. This presentation will also cover the STM32C0's power management functions and all low power modes. STM32C0 devices feature a power control unit designed to enhance flexibility in power mode management and further reduce overall application consumption. In run mode, the system clock can operate up to 48 MHz, consuming only 58 microamps per megahertz. STM32C0 devices support 5 main power modes: run, sleep, stop, standby, and shutdown modes. The flexible power management provides high performance with a core mark score of 125 at 48 MHz, along with excellent power efficiency. The STM32C0 has several key features related to power management. It offers multiple low power modes, down to 19 nanoamps, while still allowing wake-up with an event on an input-output pin. Numerous peripherals can wake up the MCU from low power modes. Dynamic consumption is as low as 58 microamps per megahertz when executing from flash memory. Thanks to these diverse power modes, the STM32C0 provides high flexibility, helping minimize power consumption based on active peripherals, required performance, and wake-up sources. The STM32C0's primary power supply is the VDD/VDDA pin, supplying all input-output pins, the reset block, temperature sensor, and all internal clock sources. Additionally, it powers the standby circuitry, including the wake-up logic and independent watchdog. VDD supplies voltage regulators that provide the V-core supply, which powers most digital peripherals, SRAM, and the flash controller. VDDA is the same as VDD and powers the analog peripherals. The VREF Plus pin provides reference voltage to the analog-to-digital converter and can be used as an external buffer reference. Flash memory is powered by 2 power rails, VDD for the memory and V-core for the controller. On the STM32C071N device, an additional VDDIO2 power supply is available, providing power for USB and other GPIOs. The primary power supply, VDD, supports full functionality in all power modes, ranging from 2 to 3.6 volts. Device functionality is guaranteed down to 2 volts, at which point a power down reset is triggered. VDDA is always connected to VDD. In some packages, a VDDIO2 supply is available, with input-output functionality guaranteed down to 1.65 volts. To use USB, the supply voltage must be between 3.0 and 3.6 volts. VREF Plus serves as the analog input reference voltage and must be between 2 volts and VDDA. When analog peripherals using VREF Plus are not active, the pin can be grounded. For packages without a VREF Plus pin, VREF Plus is internally connected to VDD. The power supply supervisor ensures safe and ultra-low power reset management. STM32C0 devices include a power-on reset, or POR, and a power-down reset, or PDR, both active in all power modes except shutdown mode. The brownout reset, or BOR, triggers a reset if the microcontroller's power supply drops below a set threshold, regardless of VDD slope. 4 thresholds, ranging from 2.0 to 2.95 volts, can be selected via option bytes programmed into flash memory for both rising and falling edges. BOR can also be disabled to conserve power. Both power-on reset, POR, and brownout reset, BOR, reset all registers. When the device exits standby mode, all registers powered by the main regulator are reset. Exiting shutdown mode triggers a full power reset. When BOR is enabled, 4 levels can be selected via option bytes, with independent configuration for rising and falling thresholds. In run mode, the CPU is clocked, and programs can be executed from flash or SRAM memory. Power consumption in run mode can be reduced by selecting a lower system clock frequency, scaling down the clock, disabling unused peripherals, or stopping their clocks through peripheral clock gating. Each peripheral's clock can be independently configured as on or off in run and low power run modes. By default, all peripheral clocks are off, except for the flash interface clock. SRAM clocks are always on in run mode. After a system or power reset, the device starts in run mode. Run mode power consumption depends on several factors: the binary code executed, influenced by the program and compiler, the memory location of the program, software configuration, I/O pin loading and switching rate, temperature, and the memory source for instructions, either flash or SRAM. Energy efficiency improves when executing code from flash memory, especially when the flash accelerator is enabled, utilizing an instruction cache and prefetch buffer based on SRAM. In sleep mode, all peripherals are usable, and wake-up is fastest. The CPU is stopped, and each peripheral clock can be gated on or off via software. Sleep mode is entered by executing the assembler instruction: wait for interrupt or wait for event. Depending on the configuration of the sleep and exit bit in the Cortex M0 Plus system control register, the MCU can enter sleep mode as soon as the instruction is executed, or after it exits the lowest priority interrupt service routine. This configuration helps save time and power by removing the need to push and pop the stack when exiting low power mode. However, all computations must occur in the Cortex M0 Plus handler mode, as thread mode is no longer used. In sleep mode, the CPU clock is off, and the system clock can operate up to 48 MHz. By default, the SRAM clock remains enabled, but can be gated off via software during sleep mode. Sleep mode power consumption is 17 microamperes per megahertz with flash memory active. Flash memory can be powered down in sleep mode if the FDPSLP bit is set to 1 before entering sleep mode. Stop mode is the lowest power mode that retains full system state, with only a 2.5 microsecond wake-up time to run mode at 12 MHz. SRAM contents and all peripheral registers are preserved. All high-speed clocks are stopped, but the 32.768 kHz external oscillator, LSE, and 32 kHz internal oscillator, LSI, can be active. Some peripherals can be active and wake up the system from stop mode. On wake-up, the system clock is the internal high-speed oscillator at 12 MHz, with a 2.5 microsecond wake-up from RAM or 5.9 microseconds from flash, keeping the sys clock divider configuration upon wake-up. All clocks in the vCore domain are stopped, and both HSI48 and HSE oscillators are disabled. The real-time clock, RTC, which is clocked by the internal or external low-speed oscillator, remains active. The brownout reset BOR is always enabled. Most peripheral clocks are gated off, but several peripherals like USART1 and 2 I2C1 and the independent watchdog can still function in stop mode. Interrupts from active peripherals or events on any input-output pins can wake up the system from stop mode. USART1 and 2 and I2C1 can temporarily enable the HSI48 oscillator during stop mode to detect a wake-up condition. If it's not a wake-up frame, The HSI48 clock is used only by the requesting peripheral and then turned off. Typical stop mode consumption is 80 microamps at 3 volts when HSI is off and 605 microamps when HSI48 is on. Standby mode is the lowest power mode that allows retention of context information in 4 PWR backup registers. In this mode, voltage regulators are powered down, and the contents of SRAM and peripheral registers are lost. The ultra-low power brownout reset BOR remains enabled to ensure a safe reset even if VDD slopes. Each input-output can be configured with or without a pull-up or pull-down resistor, controlled by the APC bit, to manage external component states during standby mode. 5 wake-up pins are available to bring the device out of standby mode. The polarity of these pins is configurable. The wake-up clock is HSI48 divided by 4, resulting in a 12 MHz frequency. In standby mode, the voltage regulator is powered down, but the RTC, clocked by the internal or external low-speed oscillator, may remain active. The brownout reset can be enabled, and the independent watchdog can remain active in standby mode. The device can exit standby mode through a reset, brownout reset, power down reset, independent watchdog reset, or any event on the 5 wake-up pins. Typical standby mode consumption without the RTC is 7.45 microamperes at 3 volts. The shutdown mode is the lowest power mode, consuming only 19 nanoamps at 3 volts. This mode is similar to standby mode, but it lacks power monitoring, as the brownout reset BOR is disabled. As a result, the microcontroller's state is not guaranteed if the power supply drops below 2 volts. The low-speed internal oscillator, LSI, is unavailable, and consequently, the independent watchdog is also inactive. A brownout reset is triggered when the device exits shutdown mode, resetting all registers and generating a reset signal on the pad. The available wake-up sources are the 5 wake-up pins. Upon waking from shutdown mode, the wake-up clock is HSI48 divided by 4, which is 12 MHz. In shutdown mode, the voltage regulator is powered down, and the brownout reset BOR is deactivated. The wake-up sources are limited to the reset input and the 5 wake-up pins. This slide provides a summary of all the power modes in the STM32C0 family. The device can transition from run mode to any low power mode, and from any low power mode back to run mode. However, transitioning directly from one low power mode to another is not possible. There are 3 bits available in the flash option bytes to prevent entry into specific low power modes. One option bit, when cleared, configures reset generation when entering shutdown mode. Another option bit configures reset generation for standby mode, and the final bit configures reset generation when entering stop mode. The microcontroller includes special means for debugging software in low power modes. By default, stop, standby, and shutdown modes disable FCLK and HCLK, making debugging impossible. However, in sleep mode, the device keeps both FCLK and HCLK active. To maintain these clocks and preserve debug functionality in stop, standby, or shutdown modes, the debugger must set the DBG stop bit for stop mode, or the DBG standby bit for standby and shutdown modes in the DBG MCU CR register before entering one of these low power modes. When the appropriate bit is set, the regulator remains on in standby and shutdown modes, and HCLK and FCLK clocks are supplied by an internal RC oscillator. This allows the connection with the debugger to remain active during low power modes, enabling continued debugging after wake-up. It is important to remember to clear these bits when the microcontroller is not being debugged, as they increase power consumption in low power modes. To complement this presentation, you may refer to the following topics: reset and clock control, interrupt management, peripherals with wake-up from stop capability. This table compares the power control features of the STM32C0 with the STM32G0. The STM32C0 supports only one stop mode, while the STM32G0 supports two. In standby mode, the STM32C0 retains only the backup registers, whereas the STM32G0 also retains SRAM. The STM32C0 does not support VBAT mode. Additionally, sampling mode for brownout and power down reset, BOR and PDR, is not supported by the STM32C0. In stop 0 or 1 and standby modes, the power on reset, POR, and power down reset, PDR, can be periodically activated in the STM32G0 to reduce power consumption. Thank you for attending this presentation.